Hello everyone, I'm Ben Adams. I'm a postdoc mechanical engineer here in the Geothermal Energy and Geofluids group at ETH Zurich, Switzerland. I'm going to talk to you today about using geologically sequestered CO2 to generate and store geothermal electricity. It's a technology we call CO2 Plume Geothermal, or CPG. I'm going to talk to you a little bit about previous publications that we made in this field and ongoing research that we also published in the proceedings for this MITAB20-215 conference. Co-authors for this work are Professor Martin Osar and Jonathan Ogland-Hand here at ETH Zurich, and Professor Jeff Belicki at The Ohio State University, and Mark Fleming in the University of Minnesota. CO2 Plume Geothermal, or CPG, circulates permanently stored CO2 to generate electricity. On the left here, you see a diagram from our recently submitted paper. It shows this sedimentary reservoir deep within the ground, say 2 to 3 kilometers, where CO2 has been stored as a part of climate change mitigation. Once the CO2 is down here in this naturally porous media, it gets hot. The hot CO2 then is produced up to the surface through a production well. It's expanded through a turbine, generate electricity. It's cooled, pumped, and then re-injected back down into this deep reservoir. In our 2015 paper, we found that at moderate depths, say 2.5 kilometers, the power generated from a CPG system, which are these black lines here, is much greater than the power generated from a traditional brine geothermal system using an ORC, which are the orange lines here. This is because CO2 has a lower viscosity than water, but a similar heat capacity. So basically, it can extract the same amount of heat as water, but with a lower resistance to flow, which just makes it easier to extract heat. The CO2 is also compressible, which means its density changes a lot. So the CO2 in the production well here has a much lower density than the CO2 in the injection well. This facilitates a thermosiphon, which can circulate the fluid on its own without even a pump. But we do find that if you add a pump, you can generate more power. Lastly, CO2 has a low mineral solubility, lower than water, so it sidesteps these issues that water geothermal systems have of precipitation, which can be troubling. The CPG is installed in a sedimentary basin where CO2 is sequestered to provide a return on the stored CO2. This is so-called carbon capture utilization and storage, or CCUS. These sites for CO2 storage are located all over the United States, here on the left, and all over the world on the right. So once you have the CO2 within the ground, it basically unlocks this ability to generate geothermal electricity with that reservoir using CPG. And the simulations that we run are just use regular reservoirs with a 35 C per kilometer temperature gradient, which is the average for the western half of the US. So you don't need any special geology to do geothermal. The work that we've done in the proceedings paper is to update the CO2 reservoir model and the power generation curves. So in the past, we've used a 5-spot reservoir on the left that we've simulated with TUF2. And TUF2 is a very good simulator for finding transient responses of pressure and temperature. But we found that we were really only looking for the power generation in the first decade or so of a power generation of CPG. So really, we could replace it with an analytics solution and make the computation and simulation of the system a lot easier and get just more results to see what the parameter space looked like. And this is highlighted in the proceedings paper as well. This is the analytical solution for the reservoir impedance as a function of reservoir properties, etc. On the right, you see the power generated, the contour plot for CPG, for CO2, CPG, and water geothermal systems. The CO2 is in orange and the water is in black. This is for different reservoir depths and transmissivity. The transmissivity is just the product of the permeability and the thickness of the reservoir. And this is all for a 35 C per kilometer temperature gradient, which is an average one in the western US and common throughout the world, and a 41 centimeter well diameter. The magenta star indicates our base case, which is a 2.5 kilometer reservoir with 50 millidarcy and 300 meter thickness. Like our past publications, we found that as depth and transmissivity increase, so does power. And we find there's a crossing of the CO2 and water power generations at about 10 megawatts here. Below that, at lower transmissivities and depths, the CO2 does a better job generating power, and at higher powers than that, the water does a better job, basically because of the high specific heat of water. It can extract a lot of energy. And we've also found for minimum thresholds with the minimum threshold where you can generate, say, 100 kilowatts of electricity for water in red and CO2 in blue. So the CO2 can generate electricity at much shallower depths and moderate transmissivities than the water can. This power generated is for a 5-spot, 1 kilometer square system, and you can upscale it to your reservoir size from there. Lastly, energy storage can be added to a CPG system, which we call CPG Energy Storage, CPGES. This is from our 2018 publication at Stanford Geothermal Congress. Basically, in addition to your deep reservoir here, which you need for CPG, you can add a shallow reservoir at, say, 1 kilometer depth, and you can operate the system in 2 modes, generation and storage mode. So in the generation mode, you produce CO2 from this deep reservoir to the surface. You spin your turbine, you cool it a little bit if you have to, but then you store it in an intermediate state in your shallow reservoir. And this basically you have no parasitic loads here, so you're mostly just generating electricity. Then later, when power is available on the grid, you can produce the CO2 that you temporarily stored in your shallow reservoir. You can do the cooling and pumping on it that you skipped in the generation step, and then re-inject it back into your deep reservoir, so you can provide peak generation when it's needed, and then do your storage when there's energy available on the grid, say from excess wind or solar. If you'd like to know more about our project, you can visit our webpage in the Geothermal Energy and Geofluids group. Thanks for listening.